equations contain two or more variables, and it's often useful to use these equations and solve them for a specific variable. In real life, we often frequently need multiple variables. If you think about situations like running a company, running a government, a budget, there's a lot of things going on at once. You have income coming in, interest rates, stock market, and if you're trying to figure out how all these things play in, it's going to take more than one variable. So sometimes when working with these equations, we have an equation and we want to solve it for a variable such as x or y, and we're going to talk about how to approach that. The strategy is to isolate the variable that you want to solve for using the techniques that we've previously learned. For example, the addition technique, subtraction, multiplication, division. Before, we were just isolating a variable such as x or y from numerical values like 2, 4, 5, 6. Now, we're not only going to be separating out a variable from those numbers, we're also going to be separating out a variable from other variables. A typical application of this would be being asked to solve a formula for a different variable. If you look at an equation such as y equals 2x plus 3, it's already solved for y, but you might be given a problem where you're given this equation and you're asked to solve for x. To do that, you would go about it the same way as before, where you're isolating the variable that you want to work with on the left side. But this time, in order to do that, you've got to not only move numbers over, you might have to move variables over as well. Looking at this again, y equals 2x plus 3. In order to move the x to the terms containing x to the left side, I have to first subtract both sides by 2x. Y minus 2x equals 2x plus 3 minus 2x. Now I have my x containing terms on the left side where I want them, but I've still got a situation where I have a y over here that I don't want. So what I'm going to do is move other variables and numbers to the right side. And it really doesn't matter which side you do as long as they're isolated, but by convention we put the term that we're solving for on the left and everything else on the right. To move the y over to the right side, I'm going to subtract by y, subtract both sides by y. The y's cancel out, and then I have minus 2x equals 3 minus y. Using our typical technique where we divide, if it's multiplication, we're going to divide in order to isolate the variable. So I'm going to divide both sides by a negative 2x. And I'm going to see that these negative 2's cancel out. Shall we correct that just by negative 2, not by negative 2x? So negative 2x divided by negative 2. The negative 2's cancel out, and I'm left with x equals 3 minus x over negative 2. Okay, so in order to solve this for x, what we have to do is move the variable that we're solving for, x, to one side. So I'm moving the terms containing x to the left, and then I had to move the other terms, in this case y, over to the opposite side. Once I have that done, I can finish isolating the variable by dividing both sides by negative 2. And then a similar example asks you to solve for y when given the equation 7x minus 4y equals 15. The first thing that I need to do is move the term I'm solving for to the left side. And I see that there's only one term containing y, and it's already on the left side, so that's done for me. The second thing I'm going to do is move all the other terms to the other side of the equation, to the right side. So I need to move 7x to the right side of the equation. I'm going to do that by subtracting both sides by 7x. The 7x's cancel out, and that leaves me with minus 4y equals 15 minus 7x. In order to isolate the y so that I can solve the equation, I'm going to divide both sides by negative 4. On this side, the negative 4's cancel out, so I have the y isolated. And on the right side, I have 15 minus 7x equals divided by negative 4. Divided by negative 4. Again, start out by moving terms containing the variable you're solving for to the left side. Or to either side, but as I said, it's ideal to move it to the left side. Then move other terms to the right. Finish isolating the variable. For example, here we still had to isolate this term, negative 4y. We had to isolate the y. In this example, we've been asked to solve for q. 2p minus 6pq equals q minus 10. Since I'm solving for q, I want to get terms containing q on the left. And I see that I have a q over here on the right, so subtract both sides by q in order to move that q to the right. So I have 2p minus 6pq minus q equals negative 10. Looking down here, I have all my terms containing q on the left, but I also have a term that doesn't contain a q over there. I have 2p. I want to move that over to the right side. In order to do that, subtract by negative 2p. That leaves me with negative 6pq minus q, the 2p's cancel out, equals minus 10 minus 2p. Now, I need to separate these q's from the negative 6p, and I can do that by factoring. And as I mentioned earlier in the course, factoring is taking the distributive property and working in reverse. Remember that the distributive property says that a times b plus c equals a times b plus a times c. If I'm moving in this direction, that is using the distributive property, distributing the terms. If I go the other way, it's called factoring. And what factoring does is it allows us to separate out that variable that we want, which is q. So what I'm going to do is I'm going to pull this q out from here using factoring. The way I can double check to see that I factored correctly is I can use the distributive property to make sure that I get my original term back. So q times negative 6p is negative 6pq. Q times negative 1 is negative q. So I factored correctly, and I'm allowed to do that with this. So negative 10, the right side stays the same. What this has done is allowed me to separate out this q. Once I've separated out the q, I can move this term over, this expression over, by using my usual method. And since this expression is multiplied by q, I'm going to use division to move it over to the other side. Q times minus 6p minus 1 equals negative 10 minus 2p. Divide both sides by negative 6p minus 1. This cancels out, leaving me with Q equals minus 10 minus 2p minus 6p minus 1. Now, there's a lot of negative signs in there. However, I can change this because if I multiply both the numerator and the denominator by negative 1, I can simplify it into 10 plus 2p over 6p plus 1. And then I'm going to put it into more of a standard form, in which we put the variables first. 2p plus 10 over 6p plus 1. If you got this far, you did the vast majority of the work. The rest of this is just cleaning it up and making it look nicer. This one was kind of complicated because it involved factoring. Looking back, we started out with 2p minus 6pq equals q minus 10. In order to solve this, I had to first move any term containing q to the left. I did that by this step, and then I moved my 2p over to the right since that does not contain a q. That left me with minus 6pq minus q equals minus 10 minus 2p. To go further with this, I needed to separate out the q, and I did that by factoring, which gave me q times minus 6p minus 1 equals minus 10 minus 2p. Now that I was down this far, all I had to do to isolate the q is divide both sides by negative 6p minus 1, which left me with q equals minus 10 minus 2p minus 6p minus 1. Putting that in a slightly different form, 10 plus 2p over 6p plus 1, and then switching the order of these two terms so it's more of a standard form gives me my final answer. In this example, I'm being asked to solve for h, and I actually recognize this as the symbol, as the formula for the surface area of a cylinder. S equals 2 pi RH plus 2 pi r squared. Remember that when I'm solving for a particular variable, I want to get that variable isolated or moved over to one side. So I'm going to move all terms containing h to the left side. And I'm going to move all the other terms to the right side. So I'm going to move terms containing other variables and numerical terms to the other side. Now, I could go about this and actually isolate the h right here on the right, but by convention, we do it the other way, so I'm going to rewrite this. 2 pi RH plus 2 pi r squared equals s. So now I have my h on the left. That's already done. All I did is to reverse the order of the two sides of the equation. The next thing that I need to do is to remove all the terms on the left side that do not contain h. I'm going to do that by subtracting. I have 2 pi r squared, and I'm going to subtract 2 pi r squared from both sides. And that's going to give me 2 pi RH equals s minus 2 pi r squared. Okay. Now I'm just left with one more step. I have to isolate the h by dividing both sides by 2 pi r. These cancel out, and now I have h alone equals s minus 2 pi r squared over 2 pi r. Looking back, I was asked to solve for h, and just so that I'm doing things the same way every time, I want to put the variable I'm solving for on the left. And the quickest way to do that was just to rewrite the equation so that 2 pi r h plus 2 pi r squared was on the left equals s on the right. Then I saw that I had a term over here that did not contain h, so I subtracted it from both sides to move it over to the other side of the equation. That left me with 2 pi r h equals s minus 2 pi r squared, and at that point I simply had to divide by 2 pi r in order to isolate h, and this is my answer. We have x plus y over x minus y equals 6y. So I'm going to start out by multiplying both sides by x minus y. That makes the left side a lot more simple. I have x plus y equals 6y times x minus y. I'm going to use the distributive property and change the right side to 6xy, 6xy minus 6y squared. So now I have an x on the left side, I have an x on the right side, and I need to have all the variables that I'm solving for together on one side. Next thing I'm going to do is move the 6xy to the left through subtraction, subtracting both sides by 6xy. Okay, this gives me x plus y minus 6xy equals negative 6y squared. Coming up here, rewriting this, x plus y minus 6xy equals minus 6y squared. The next thing I want to do is get this y on the left side over to the right. So first I have all my x's on the left, or terms containing x's on the left, and I want to get this y over to the right, and then I'll separate that y out in a minute. That one's a little bit trickier to separate out. X plus y minus 6xy minus y equals minus 6y squared minus y. Okay. Now I have x minus 6xy equals negative 6y squared minus y. My x's are all on the left, but I still have a y over here. And again, the way to separate something out in this situation, the way to separate out the variable that you want, is through factoring. If I look, I have an x in this first term, and I also have an x in the second term. So this would be equivalent to x times 1 minus 6y. And I'm going to double check it to make sure I did it correctly by multiplying back again. X times 1 is x. X times negative 6y is negative 6xy. So now that I have the x separated out here, I can move this term over to the right side. I'm going to handle that just like I usually do by doing the opposite operation. So I'm going to divide by 1 minus 6y. Divided by 1 minus 6y on both sides. These cancel out, and now I have x equals minus 6y squared minus y over 1 minus 6y. So this one was pretty complicated. When you started out, you had x plus y over x minus y. And the first thing I did was move this term over to the right side and then use the distributive property to change it into this form. X plus y equals 6xy minus 6y squared. After that, I moved the last term that contained an x over to the left side, and I saw that there was a y here that could easily be moved to the other side. At that point, I then got about as far as I could get without using factoring. So then I factored the x out of this expression, which allowed me to divide both sides by 1 minus 6y. That canceled those two terms out and isolated the x on the left and gave me my final answer.